Okay, so my topic will be now sampled values. Not the first time that I talk about this, and people who have seen presentations from me might again recognize the one or other slide, but I want to roll up the whole story for you again. So what will we have in the next half hour? I will go with you along the history of sampled values. By doing so, we will come across a couple of milestones. And at the end, we will look at the most recent impacts that we got from the developments and what that means for us when dealing with sampled values. Now, just for those who do not yet know what sampled values are and what they are meant for, and I assume that most of you are already familiar with at least the idea. Here, a picture how this should work. We have the signals from the process, labeled here the primary values, that are picked up by some sensors, and these sensors deliver their signals to a merging unit. And in this merging unit, the analog to digital conversion and the proper timing and the packing into Ethernet packets is performed. And then what's the output of the merging unit are the sampled values. These are sent on the substation network. In this case, it will be most likely what we call a process bus. And over this network, these data are then distributed to the consumers, which are mainly protection relays. And you see we have here a one-to-many relation. So the system does not restrict how many relays could subscribe to a sampled value stream from a merging unit. Now, how did this come along? And it has quite a story behind it. And it started almost 20 years ago when IEC 644-8 was released. So when we say start, obviously this development of this standard was even earlier than the release date. We have clearly 20 years of sampled values history starting here on the left of this slide. Now, what was this standard? 644 was the instrument transformer standard at that time. What was this part about? It was about merging units, actually. But it was restricted by the boundary condition of its time. So they had 16-bit microprocessors available at that time. And the thinking of what can be achieved was very much driven by these technology restrictions that they had. By the way, this was very similar with the development of the IEC 60870-5 standards for communication in substations, only that they had 8-bit microprocessors when they started working on that. But there were some things that survived this very early standard. For instance, the term the dataset. This is this collection of data that you send out from the merging unit to the relay. And also another term was coined already here, the term of the merging unit. You see here a snippet out of the standard where we have this box taking in the sensor signals and creating the digital output, which is the merging unit. Now, very briefly after that came 61850-9-1, and it ended in a dead end, as indicated here. And it was also a very political thing. So the 644 makers were a bit offended that 61850 did now something similar. So this could not be disregarded. And so we had this 9-1 thing, which was very strongly leaning towards 644-8. And there were still a lot of skeptical people there about this idea with the process bus and so on. And all of this went into this kind of standard. It used this universal data set. So to the honor of the 644-8, but it went to Ethernet. But there were some people who insisted that this must be used only as point-to-point Ethernet. And you see here this title, sampled values over serial unidirectional and multi-drop point-to-point links. Really, I did not make up this title. I couldn't have made up this title. It sounds not very consistent to me, but the idea behind it was don't use a bus, make point-to-point connections. And actually, you could not restrict this because the output was Ethernet, and you can use Ethernet in a bus system, no technical restrictions against that. And on the other hand, when you have switched networks, every Ethernet connection or device connection to a switch is a point-to-point connection. So what's about that? Yeah, anyway, luckily it was deprecated and withdrawn in 2012. So we got rid of that, but it's part of our sample value history. And then the first 9.2 edition 1 came up. Now what's 9.2? 9.2 is the way of really doing the 61850 way. So not thinking first, what kind of processors or networks do I have available? First, there was this abstract service defined in part 7.2. There is defined what sample values are and how this should do with all the control blocks and those things, this abstract service interface. And in part 9.2, it's just said, and this is how we do it on Ethernet. And it was done by using Ethernet multicast messages. I do not explain here exactly how this works. There are other materials also from this very event available where you could look this up. I just skip over this. Now, very closely timed to this 9.2 edition 1, there was a document released which is called or nicknamed in the industry as the 9.2 LE. And what was the rationale behind this 9.2 LE? It is the UCA Implementation Guideline, and it's actually a profile on IC 61850-9-2. And the whole idea behind this profile was to restrict the variance, because the standard itself just did tell you how to select a sample rate or how to assemble a data set. But it did not tell you which data set, and it didn't tell you which sample rate. And it didn't even tell you how to code the data in the data set. And of course, this would have caused a lot of interoperability issues if every vendor on any end would have picked his set of parameters that he has chosen to support. And it is not imaginable that all this implementation would have covered a range of parameters that would totally also cover those parameters of the other vendor on the other end of the communication link. So there were some smart people seeing this very early, that there needs to be something like this profile to actually almost enforce interoperability. And this was the reason of this document. Now, what did this document agree to? They wanted to make something which was good for protection and metering. And there was one data set defined, which is today still known as the 92LE dataset. It has 4 voltages and 4 currents, so the phase quantities and the neutral quantity. And this had the advantage that you could just hard code this. There was no configuration involved in this. There were sample rates at that time specified still in samples per period. And we will focus on these 80 samples per period, which is good for protection and metering. And the power quality version was also defined, but we will not go into this. And since we did not have anything better available at that time, a pulse per second over optical fiber was chosen as the time synchronization method for the merging unit. This was a rather exotic solution, and in the end, it also showed to be a kind of an obstacle for the proliferation of this technology. Just to give you an order of magnitude, here are some characteristic figures for this protection and metering variant with a specification of samples per cycle. We have different sample rates depending on the mains frequency. This is 4,000 or 4,800 samples per second. It was defined to send exactly 1 sample per Ethernet packet. So we have this very same packet rate on the network. And when we make the math, how much this will typically use from the bandwidth on the network, we get to 5 to 6 megabits per second on the Ethernet. So you can easily make the math that on 100 megabit per second Ethernet, you can go up to about 15 streams, and then you have loaded the network fully. Of course, you want to give some reasonable margin, but that's a rule of thumb that helps you very much to check if your network design is in line with the load that you're going to impose on it. And here you see something which I would call one of the milestones that really stick in my mind, because we met here to make a testing with servers and clients. So it wasn't about sampled values at this time, but when we put our stuff together, we briefly mentioned that we had already prototype implementation of this 92LE variant in our devices, and we just plugged the stuff together. And when you look closely at the test set that you see here next to the protection relay, you should notice that there are no banana plugs and banana cables used. So this protection test really works with sampled values and GOOS. It worked out of the box, proving that the interoperability of 92LE was really good. And this was already in September 2005. Now, a year later, at the exhibition at the CIGRÉ session in Paris, we had an interoperability demo, and there were already a couple of merging units, a couple of relays, and a test set, which was in fact also mimicking a merging unit. So we had 4 merging units and also relays from at least 3 different vendors playing in a 61850 demo system. And thanks to 92LE, all this worked together with relatively minor problems. So I emphasize on that again and again, because you should not underestimate the value that you get when you have a very tight definition with only a small number of options. You can easily get this to work. Sometimes along the way, there was the need to go into the maintenance cycle of the standard. After 2010, we had this edition 2 of IEC 61850 being published. And of course, also the part 9.2 got an edition 2. There were some extensions made, but it was not very sensational. It did not make a lot of impact in the industry because there were simply not so many implementations around, and the effect on the interoperability due to these changes in edition 2 were not very drastic. Now to the obstacles that were present around 2010, when we already had 9.2 LE in place, when we had these prototypes showing that this works well, and we were still seeing no significant progress in the industry with the adoption of the sampled values. That has to do, on the one side, with psychological reasons. The protection people are full of skeptics that were not so keen on going after this technology. But on the other side, we also had some technical reasons, because there were some problems not fully covered yet. And one of these problems was the time synchronization. As mentioned, this pulse per second over optical fiber was not an optimal way of doing it. It lacked many possibilities, and also there were not many devices around just delivering this kind of signals. And another aspect was network redundancy. Especially when you deal with sampled values, you cannot allow packets to get lost, because that would interrupt the information flow from the sensors to the relay. And this network protocols with redundancy were just coming up roughly around the year 2010. We got solutions for that, but this was still evolving or even not yet existing when we did 9.2 LE. Now, what did we get in turn to solve these shortcomings and to remove these obstacles? In the meanwhile, the precision time protocol, IEEE 1588, had made its way into our industry. It's really a very elegant solution. We can distribute time via the Ethernet. We do not need an additional infrastructure for doing that. And most of all, it was just accurate enough for our purpose, or let's say more than accurate enough, because we can easily get in the range of 1 microsecond of time error, which is just perfect for that what we want to achieve. And on the other hand, there were some definitions made that made this IEEE 1588 standard even more applicable for the electrical power industry, also selecting a limited number of options. And we got this IEEE profile, and then later on also 61850-9-3, which restrict the variants that you have to consider for time synchronization. So when you go for time synchronization in a substation, you would insist that one of those profiles here would be supported. Now, for redundancy, 61850 also looked around what is available. The working group did luckily not intend to invent something on its own. And there was something very promising going on in TC65 of IEC. On the industrial network side, there were redundancy protocols developed inside the standard 62439. And in the part 3, we had the PRP and HSR protocols defined. Parallel redundancy protocol and high availability seamless redundancy. These two protocols are basically very different from each other. The one is a duplicated network, the other one is a special ring structure. They both have their cons and pros that I'm not engaging in here now, but nevertheless, we now got with these two protocols what we needed for the sampled values. We could ensure that there is no packet loss when there is a single failure in the network. So this problem was solved. Nevertheless, there are still some things to consider when you pick the one or the other. And just to mention one thing that we run across just recently, again, is the question, how do we run the precision time protocol over these redundant networks? So this is not fully understood yet. You have to look there carefully to get a good time synchronization system. And you should also look into this already when you do the network design and not just being surprised when you switch the stuff on. Now some more recent milestones. I just picked 4 projects that made it to the conferences, so to say. A project that were presented by the responsible people on international conferences. There are more projects than this, but they are somehow role models for what we have seen in the last 10 years, probably. And when you see here some time ranges a year from to, it might be a discussion with people more involved in these projects when they really started and when they really considered it to be finished. But at least this time ranges here is when we saw it as, when we saw most of the things going on and most of the questions asked and most of the issues discussed around these substations. So this is the Poste Intelligent in France, the Avon substation near Sydney in Australia. A very nice paper has been presented about that, also touching on many other things, not only sampled values in this regard. In Norway, Statnett built this full set station with sampled values. And there was this fitness project at Scottish Power, which was very prominently presented and where OMICRON was also very heavily involved in helping in the testing. And Priyanka Mohapatra, who will make the last presentation in this afternoon, she was the project manager of this fitness project. And she went along with us in this project very tightly, and many of the experiences she made is what she now brought into what she will present to you later on. Yeah, in 2016, there was another thing upcoming. 61869 was in the making. And actually, this is the new instrument transformer standard. 61869 is to supersede 644. And there is one part, -9, and this is not by accident. They have aligned it with the -9 of IEC 61850. This -9 part of 61869 is about sampled values. And what did they do? And I just break this down here on this table to highlight the one or other thing. They defined a couple of new variants. So why do I think this has been done well? Also, the variants have been extended because the picks were quite reasonable. First of all, what we have here in the list on the top is what we already had in the 9.2 LE profile. 9.2 LE wasn't a standard. It was just an implementation guideline, more or less a recommendation. And 61869-9 has taken these variants from 9.2 LE in here and made them, so to say, a part of their standard. Then there were two new preferred variants defined, and I think they were smartly chosen. You see here, we went away from this samples per cycle or samples per period concept that gives different sampling rates depending on the network frequency. We have now fixed frequencies for the sampling, and the samples per packet were aligned in a way that both of these variants for protection and for power quality have the same packet frequency on the communication network. This is a quite nice approach. And there is another variant, I don't talk about that, but let me briefly jump back. We have a sentence here, down here, says the standard was open towards using configurable dataset. This was already touched in that standard. Also, it started off with the 9.2 LE dataset, but this is something that we will come back to later on. And not so long ago, last year, we then had edition 2.1 of 9-2, and this brought also some things that have an impact on that what will happen, hopefully in the future. So the new issues that we have now are the configurable datasets, and actually 9-2 did always allow to configure datasets, but it was the implementation guideline that said, no, we don't use these variants. We use this one fixed dataset. And as said, 61869-9 suggested to go beyond that. And then there is this topic of optional fields that we had already all the time, but 9.2 LE also said we will use one of them, the sample sync, and we will not use the others. And so it went almost unnoticed that there were these optional fields around all the time, but we simply didn't see it as optional. We had a very clear definition what to use and what not to use. Now the configurable datasets allow to adapt the dataset to the use case. You could strip down it to contain only 3 currents, which would be good enough for a Bay merging unit for a busbar protection. Or you could extend the dataset. 61869-9 suggests to go 24 values, but we have now seen implementations going up to 32 values per sampled value stream. And there is hope that you can optimize the system by adapting the dataset, either to save bandwidth or to come down with the packet rate or the number of sampled value streams or whatever you find important in your case, but we will come also back to this. Because you always have to ask yourself, why am I going to optimize something? And there is always this trade-off. Alex also indicated when you have configurability, you have to configure, you have to test, you have to maintain that. And this can be costly on the other side. So when you try to gain some technical advantages by configuration, you have to be aware that on the other side, the configuration efforts can be very costly. And unfortunately, protection engineers tend to look more on the configurability and not at the efforts you have with it. And sometimes they seem to me penny wise and pound foolish. Okay, optional fields. This is a complicated topic. I have put together what I could find in the different standards over the time and put it into this table. I'm just saying, except for the bottom two rows, everything was there already with 9-2 edition 1. 9.2 LE made some very strict definitions of what to use from it and what not. And now we have, with edition 2 and edition 2.1, we got some new ones. Let's quickly look into this. We already had the sample sync. One of the new ones that is now to be considered is this refresh time, but I think not for the protection people. Maybe when we use that for synchrophasers, you're not sending a fully qualified timestamp 4,800 times per second. Most important maybe on this list is the bottom one, the sync source ID. So this allows to send the clock identity of the clock that synchronizes the merging unit with the sampled value stream. And this can be very valuable for the relays to check if the information coming from different merging units is synchronized to a common clock. And here I'm already at the conclusions. We have this around for quite a while. And I hope these obstacles that hindered the proliferation are now removed. We have seen some pilots where the problems have been solved, more or less. But I think the most important thing that has happened recently is the change perception in the industry. There are more and more vendors now offering this really as their solution, and not just as the solution for this 61850 geeks. Telling the people still that 5 amps and 100 volts are the real thing, and the other one is only something fancy. Now, many of the people in the industry are really going for this technology, and I think this will be the reason that we will get foot on the ground with sampled values. Thank you very much for your attention.